All right, let's just dive right into this. Today, we're exploring how abstract mathematics actually acts as a sort of magic portal. A portal to solve real-world physical problems that literally seem impossible. Have you ever faced a problem so incredibly complex that tackling it head-on just leads you straight into a brick wall? Well, in physics and engineering, this happens all the time. But mathematicians have this amazing secret weapon. Instead of fighting a grueling battle in the real world, they just teleport the problem into an alternate mathematical dimension, solve it there where it's easy, and then drag the answer back to reality. It's wild. And today, we're unpacking a brilliant explainer on a technique called conformal mapping that does exactly that.
Before we jump into the deep end, here's our quick roadmap. We'll start with a steady-state heat problem, derive the governing equation, and then introduce our conformal mapping strategy. After that, we'll translate everything to the W-plane, find our harmonic function, and wrap up by calculating the final temperature distribution.
Okay, part 1, the steady-state heat problem. We're starting off in the real world with a semi-infinite flat plate of metal. Basically, imagine a massive, incredibly thin sheet of metal that stretches out forever into the upper half of a grid, and our ultimate goal is to figure out its exact temperature at any given point.
So, to establish the rules of the game here, we make 3 core physical assumptions, really just to simplify things. First up, we assume two-dimensional flow. This just means the temperature, which we'll call T, only changes based on its left-right X position and up-down Y position. We're totally ignoring the thickness of the plate. Second, we assume a steady state. So we aren't looking at the plate right after someone just blasted it with a blowtorch, right? We're looking at it after the heat has had plenty of time to settle and remain perfectly constant. And finally, third, there are absolutely no hidden heat sinks or heat sources secretly buried inside the metal itself.
Moving on to part 2, deriving the governing equation. To actually translate our physical metal plate into the language of calculus, we first have to figure out how the heat is behaving at a microscopic level. Just picture a tiny rectangular piece of our plate. We can actually measure the heat flowing in and out of it using Fourier's law. If you consider a little rectangle with a width of delta x and a height of delta y, you know that heat has to flow across its left and right faces as well as its top and bottom faces. And because we already assumed a steady state, where temperatures aren't fluctuating over time, the net rate of heat loss from all 4 of these faces has to perfectly balance out to 0. The heat entering must exactly equal the heat leaving.
By balancing that flux across the rectangle, we hit a bit of a wall. We find that our temperature function absolutely must satisfy what's called the Laplace equation. In calculus terms, the sum of the second partial derivatives of our temperature with respect to x and y has to equal 0. And when a function perfectly balances out like this, we call it a harmonic function. Now, finding a harmonic function is totally fine in theory, right? But to solve it for our specific metal plate, we have to apply our physical boundaries. And honestly, this is notoriously tricky. Our real-world boundaries are incredibly messy and fractured, making this Laplace equation virtually impossible to just solve head-on.
Which brings us to part 3, the conformal mapping strategy. This is exactly where we need a mathematical translator to escape those impossible physical boundaries. We desperately need a way out.
Okay, let's look at this 4-step playbook. This algorithm is literally our map for opening a portal to another dimension where the math is a breeze. Step 1 is defining our portal, an analytic mapping function that takes us from our physical world, the Z-plane, over into an abstract mathematical dimension, the W-plane. Step 2 is sending our impossible boundaries through that portal to see what they look like on the other side. Step 3 is actually solving the heat problem in that new, much simpler W-plane. And finally, step 4 is grabbing that solution and dragging it right back through the portal into our physical Z-plane.
Now, we are totally forced to use this strategy because our real-world boundaries on the Z-plane they're fractured and complex. Picture the bottom edge of our metal plate sitting directly on the x-axis. The problem states that the temperature is kept at exactly 1 degree for the segment between -1 and +1. But for literally everything outside that segment, less than -1 and greater than +1, the temperature abruptly drops and is fixed at 0. This fractured, jumpy boundary condition right on the edge of our plate makes the calculus an absolute nightmare.
So let's jump to part 4, translating to the W-plane. Let's actually execute step 1 of our playbook and see how this builds as we teleport into the abstract math dimension.
Here is how the transformation works in action. On one side is our messy physical Z-plane, with temperatures awkwardly jumping between 1 and 0 along the bottom axis. But by using a carefully chosen logarithmic function, specifically the log of z minus 1 over z plus 1, we can completely stretch and warp our messy semi-infinite plate, And what emerges in the W-plane is this incredibly neat infinite horizontal strip. The fractured pieces of the x-axis are smoothly mapped onto two perfectly parallel continuous horizontal lines. It's like magic.
Comparing these two dimensions side by side really puts it into perspective. Notice how the complex, fractured boundaries in reality become these incredibly clean, uniform boundaries in the W-plane. Back in our physical Z-plane, the boundary was this single broken line with jumping temperatures. But over in the W-plane, our boundaries have morphed into two separate, continuous lines. A bottom line at V equals 0, where the temperature is 0, and a top line at V equals pi, where the temperature is exactly 1. We've literally separated the messy jumps into two clean, distinct parallel walls.
All right, part 5, finding the harmonic function. Now that we are safely tucked away inside the W-plane, we can easily tackle step 3 of our playbook.
Because our boundaries are perfectly flat and parallel here, slaying the mathematical dragon is astonishingly simple. We just need a function that is 0 at the bottom wall and 1 at the top wall, which sits at a height of pi. So our harmonic function, h of uv, is just this incredibly clean linear equation, v divided by pi. That is literally it. In this abstract dimension, the heat simply scales perfectly linearly from the bottom to the top. No complex calculus required whatsoever.
And finally, Part 6, the final temperature distribution. For our last step, we get to grab our hard-won prize, that beautifully simple equation, and step back through the portal into the physical world.
By taking our simple W-plane equation, v over pi, and substituting our original physical x and y variables back into it, basically throwing that logarithmic transformation in reverse, we get this beautifully complex final expression. The temperature T at any point x and y on our physical plate is equal to 1 over pi times the arctangent of 2y over x squared plus y squared minus 1. We actually did it. We have a single, clean formula that instantly tells us the exact steady-state temperature anywhere on that original, seemingly impossible, semi-infinite piece of metal.
This completely reveals the physical reality of our result. If we take that final formula and set the temperature to a constant value, let's say exactly 0.5 degrees, we can graph precisely where on the plate that specific temperature sits. These are called isotherms, literally lines of equal heat. By graphing these out, they form these perfect geometrical curves, showing us exactly how the heat gracefully flows and radiates from the hot segment of our metal plate out into the colder regions. What started out as an impossible boundary condition resolves into this beautifully elegant map of heat flow.
So, conformal mapping isn't just some clever algebra trick. It's really a completely different way of seeing reality. It teaches us that when a problem seems utterly unsolvable, the flaw might not be in our abilities, but in the dimension or perspective we're using to look at the problem. By creating a portal to warp the space itself, the impossible actually becomes trivial. So, I'll leave you with this. What other impossible physical problems could we solve? What else could we unlock in physics, engineering, or even our daily lives, simply by shifting our perspective and translating the universe's messy geometry into elegant, new mathematical spaces? Thanks so much for exploring this explainer with me today.